Here's a development of the surface area formula for a solid of revolution and an example. So if we take f of x equals x squared and revolve it around the x-axis from x equals 0 to 1/2, then you get this figure over here to the left here. And our goal is to find the surface area on the outside. So at an x value location, just like you did in the solids of revolution, you take a vertical slice. You can call it a cut, some kind of slab. So this vertical or slanted height here is going to be very important, because that seems to matter on the surface. It's going to make the surface wider there. So let's find that first. So you go like this, you draw the picture, you realize that this is x delta x, and for the delta y, you know f prime of x is approximately delta y over delta x. Multiply the delta x over, you get this, and that means that the delta y is f prime of x delta x. Then you use the Pythagorean theorem and you arrive at your slant length there. Okay, so the arc length of the red segment is this. And then so for our particular case, where f prime was 2x, because f of x was x squared, this is the expression that you have resulting for the red segment length. Now, why does that matter? Because when you go and find the entire surface area of the whole slice, you realize the slice looks like this. And that is what's called a frustum. In this case, it's like a cone with the whole tip cut off. Sort of like a trapezoid type of idea. So the surface area of a frustum in this case is 2 pi average of the two radii times the slant length. Okay, well, we can turn this into a cylinder. We're going to take the midpoint here between the two radii and swivel that length, this side coming down here and this side coming up here. So now you have a level length the same as L. That also evens out these radii. So now you take the average of the radii and you call them just R. So that would just be, call that R. So now you have a cylinder, and the surface area of a cylinder is 2 pi r height. So 2 pi r times the height, which happens to be that L length. So the area of the surface area of the entire solid is in 2 pi r. In our case, the r was x squared, because back on the original picture, you see you have f of x being the height. And we can only say that because as the delta x goes to 0, the f of x and the which is one radius, and the other side is f of x plus delta x, those two will become equal in the limit to be f of x, because f is continuous and differentiable. So then that's your entire surface area formula. There's the slant length, and then here is the 2 pi r. Okay, and if you use Simpson 200, that turns out to be this number right here. And we'll see if we're going to do this by hand, if that's the answer we end up getting. So anyway, the general formula is here for a solid revolution. Surface area revolved around the x-axis from A to B. So back to our problem. F of x equals x squared. Here's our particular problem. Factored out to 2 pi. And now we're just working on this integral here. Use trig substitution. Set up your diagram. Tangent theta is 2x over 1. X equals 1/2 tangent theta. So dx is 1/2 secant theta d theta. And also secant is the square root, because the cosine is the 1 over the hypotenuse, and so when you turn it upside down, that's the secant, so that would just be this. Okay, then we're getting ready to do our trig substitution. So our integral under question translates everything over to this. There is your dx right there. And then everything is subbed over for right, so the x squared, here's your x. So squaring that gives you 1/4 tangent squared. And then the square root part was the secant theta, there it is. And there's the dx. So everything transforms over. Then you take your 1/4 and 1/2, that becomes the 1/8 on the outside. Multiply everything together, you get this. Then translate tangent squared as secant squared minus 1, put that there. Multiply everything together and you get this integral. We have seen previously that secant cubed integral is this answer here. Now we need to know what to do with secant to the 5th power. So if you Google reduction formula for secant, you're going to get this reduction formula right here. So that shows you how to knock the size of the exponent down. And that's proven by integration by parts. Okay, so Rn is 5, because we're doing secant to the 5th power. So we plug it into the formula. N is 5. Then you get the n minus 2, the n minus 1. That's where you're getting the 3 and the 4 from. N minus 2 is 3. N minus 1 is 4. N minus 2 is 5 minus 2 is 3. Simplify that all down, and you get this whole thing here. So then the integral we're looking for, this one here, is 1/8 of this whole thing, because you have the secant to the 5th stuff, which is all this, and you have the secant to the 3rd stuff to subtract off, and this is the answer to that. Okay, then multiply everything in, clean it up a little bit, and you get all the way to this answer. Then we're returning back to our integral now. Here was the original integral. Change out the limits to convert over to the theta. Theta is arctangent 2x. That was because tangent theta was 2x defined originally. So if x is 0, then you have arctangent 2 times 0. That comes out to be 0. If x is 1/2, then 2 times 1/2 is 1. The angle whose tangent is 1 is pi over 4. So So then we have our integral is equal to 2 pi, there's a 2 pi, times the 1/8 0 to pi over 4, which this is the new limits of your secant subtraction there. And then we already know the answer to that integral. It was all this in here. And what I did was I went up here to this step right there, and I saw that there was a lot of 64s in here and a 32, so this is 2 64ths, 1 64 and 1 64, so I factored out a 1 64th and then wrote what was left, and we're evaluating that at 0 and pi over 4. Plug all the numbers in to what they're equal to with a trig. You get this. Simplify that down, comes out to this. Then when you do your calculator and you're holding your breath, hoping you get the same answers that you did for Simpson, and indeed it comes out, in this case, exact. And that matches with the numerical Simpson's method above, so that means we did this the whole process correct.